like, share, and subscribe to my YouTube channel. Thank you for your support. Hello guys, welcome back to this YouTube channel. This is Jonathan Goldfish. Alright, I believe that it's been a long while. We haven't continued the syllabus of the pure mathematics one. So here is it today. So for this video today, we are going to enter the new chapter, chapter 5, trigonometric. Okay, let's dive into the topic now. Okay, so for the triangle over here, the right angular triangle that inscribes inside the Cartesian plane. Okay, so what's the characteristic of the right angular triangle? It has the horizontal distance, vertical distance, and of course it has the longest distance. Okay, this one we call it as adjacent side. For the vertical one, it is called opposite side. Why? Because of this side does not touch the angle, but the horizontal side does. Okay, as well as this longest length, we can call it as hypotenuse. Okay, with the angle subtended over here, as well as the right angular over there. That's why it is so called right angular triangle. But take a look at the degree. Okay, so the degree can be rotated in the positive rotations, which is called anticlockwise. Otherwise, it is clockwise rotation, where it is the negative rotation. So how to convert from the side to the degree? Okay, so the first but essential properties is you must have a right angular triangle. Okay, because of these fundamentals is indeed crucial. Okay, that can apply to many daily lives, many applications. Okay, so let's dive into the definition of the trigonometric ratios. So for the sine, we can express it as sine theta, which is equal to opposite to hypotenuse. Okay, so I'll explain why the sine theta cannot greater than 1 in magnitude. Okay, here is the sole reason. Because of it has the hypotenuse in the denominator, the vertical distance or opposite side is on the numerator, in the numerator. So the condition is the y can be at most r in magnitude. Alright? So for the cos theta, it is adjacent over hypotenuse as the same as the sine theta. Okay? But it is in the horizontal side divided by the longest side, which is the adjacent over hypotenuse. Also the same, the numerator can be at most r. Okay? So this for the sine and cosine. Later we will use the unit circle for the detailed explanations. Alright, for the tangent theta, it is the y over x. Or here is the change of the y over the change of the x. Okay, change of the y over the change of the x. For this, we can know is, turns out the tangent theta, the tangent is actually the gradient of the line. Okay, it's a gradient of the straight line. Alright, where its angle is elevated from the positive x-axis. Okay, elevated from the perpendicular distance. Okay, so where the theta is the reference angle, it can be only lie in the first quadrant. Okay, because of the Cartesian plane consists of the 4 quadrants that what you have learned from chapter 3's coordinate geometry. Okay, so in the radians, it is from 0 to pi over 2 rads. Okay, where the theta is the reference angle in the right angular triangle. Okay, Let's move on to the unit circle to define the trigonometric ratios. So you can see there's a unit circle that carries the radius of 1. Okay? To validate the definitions of the trigonometry ratios using the unit circles. Okay? So although mostly the angles do not have the exact trigo ratios, but some certain angles have 30-degree, 60-degree, and the 45-degree only. Because of you can use the sine, cos, tangent graphs to illustrate it. Okay, so let's explain it. To explain sine, what you can see that as it varies from here, following the arc of the circle quarterly to this point. So what you can see that the sine is increasing, which what it means? It means that its vertical distance is getting larger and larger. Meanwhile, however, the horizontal distance from here is get lower and lower, get smaller and smaller. Why? Because of its horizontal distance, or the cosine, varies from here to here. And for the tangent, it is trivial. Why? Because of tangent is vertical distance over the horizontal distance. So what you can see that its gradient. Okay, let's draw a gradient of the tangent. So you can imagine it. It is a gradient. Its tangent is a straight line. So as it goes from here to here, the gradient slowly increases. Okay? Oh, sorry, it's not gradient. It is the horizontal distance is 0 since there's no vertical component. Okay, it moves from here to here. So until here, there's no horizontal distance at this point. So which means the tangent over here is infinite. This one we will explain it further. Alright, so anyway, I have summarized the tables for you to memorize because this does not exist in your MF19. Okay, be sure to memorize all of this. Okay, this benefits in your Trigo exams. Especially you have to prove the Trigo identities. Alright, so yeah. Okay, let's move on to the positive angle then. Okay, let's move on to the next part, which is the positive angles. So, for this part, it is very essential that you should know all four of these quadrants. Okay, where the angle lies at any quadrants, what is their properties. Alright, let's discuss the first quadrant. So as you know before, we have learned the three trigonometrics, which is the sine, cosine, and tangent. Now, this is the case to explain what happens to the sine, cosine, and tangent, where their reference angle lies on the certain quadrant. So let's take a look at the first quadrant. For the first quadrant, all must be positive because each of these coordinates is light on positive x-axis and the y-axis. So therefore, this is known as the positive quadrant, first quadrant. Okay, where the reference angle they inscribe is a reference angle which is the acute angle. Alright, so let's take a look at the second quadrant. So for this is the positive y direction and negative x direction, which is known as second quadrant. Why does the sign become positive at here? Is because of the y direction is positive, whereas the x direction is negative. So therefore, I say that the rest is negative. Why the cosine is negative is because of their x direction is negative, according to the definitions of the cosine. As well as the tangent, it is also negative because of negative x direction. Alright, it's also from their definition. So the reference angle stretch from the positive x-axis, which is known as the obtuse angle. So what is the interval of the obtuse angle, which is pi to pi over 2, right? We need to put equal sign. No, not equal sign. So it's actually pi, sorry, it's from the pi over 2 to pi. Alright, or we can it's so-called 90 degree to 180 degree in order to say this angle is the obtuse angle. So refer to its reference angle, we can relate their values, okay, which of the values is the same using the reference angle and the other complementary angles. Okay, so this is known as complementary angles because of this sum of these two complementary angles to get pi over 2. Okay, when these two angles are both acute angle. Alright, so in order for this angle become obtuse angle, it must contain the complementary angle. Alright, so yeah, so next let's take a look at the third quadrant. So third quadrant is only positive for the tangent. It's because of both x and y directions are negative. So therefore, following the definition of the tangent, the negative at the both numerator and denominator can be cancelled out to get positive, and the rest must be negative because of sine. Sine is negative and cosine is also negative. Alright. So this angle that stretches from the positive x-axis, which is greater than 180 degree, we can note it as reflex angle, where the acute angle that inscribes inside the reflex angle is the reference angle. Okay, where the reference angle must be acute angle. Alright, so what's next? The fourth quadrant. Only x direction is positive, but y direction is negative. So for this fourth quadrant, we can only say that cosine is positive, the rest is negative. Okay? Because of the y direction is negative. So which means that following fundamentally, sine is usually for the vertical component. Cosine is usually for the horizontal component. Alright, this one you should know as a physics students. Alright, or the other dimensions, following the dimensions but is componented. Alright, so following these four relations, what we can conclude that sine theta, where the theta is a reference angle, is equal to the sine 180 degree minus theta. Okay, where the theta is the reference angle. So no matter how much of these two thetas, their sign is numerically the same. It's because of sum of these two are complementary angles to get 180 degree. Resemble the theta plus the another angle alpha to get pi over 2. So when these two are both complementary angles. Okay? So this is how I explained to you. If you have any hesitations, don't be shy. Can reach out to me following the context I have typed in my description below. Alright? So let's see, for the cosine is equal to the negative because of the component x direction is in opposite side. So therefore we need to put negative. Alright, in order to fulfill its number. Alright. So what about tangent? Tangent is also negative. Of course, it's following by its definition. Alright. So what about this? This is for the second quadrant. For the third quadrant, the sine theta equals to the sine of theta minus 180 degree. Okay? Where the theta is also the where the theta is the reflex angle for this case. Alright? So what about for this theta? It is an obtuse angle. So I would say apologize that this theta is not a reference angle but the obtuse angle. But in the end, this must be the reference angle as well as this one. Right? Since the theta at the third column over here that I highlighted is a reflex angle. Why is it called reflex angle? Because the angle exceeds 180 degree. Alright? For the cosine is also the negative because its x direction is opposite as well. What about tangent? Why the tangent is positive? Because of the definitions. Okay? Because tangent theta is basically like the gradient, right? Gradient of the straight line. Or gradient of the gradient of any line. Regardless of it is a straight line or a curve. Right? So yeah. As long the sine over cosine is cancelled out. This one we will explain about the trigonometric identities later. Alright, the fourth quadrant. For the fourth quadrant, okay, for the fourth column, the sine theta is also the negative, where the theta is also the reflex angle, just that the reflex angle exceeds 270 degree or 3 pi over 2 radian. Alright? So yeah, it is, which is to get this theta, you must need to convert using this one, 360 degree minus theta. So for the third quadrant, to get the reference angle, use the theta minus 180 degree. So for the second quadrant, you need to find the reference angle, you need to use 180 degree minus the obtuse angle. Alright? As well as for the other functions. Alright? So for the cosine is positive because the x direction is positive. Alright? So for the tangent theta, it is a negative. As I said, using the definitions of the trigonometric ratios. Alright? So yeah. So as I implied over here, the theta angle is greater than 90 degree or pi over 2 radians. Alright? Where the theta is an angle, okay, the reference angle, or the particular angles like obtuse angle and the reflex angle for each respective quadrant. Alright? So yeah, let's dive into the trigonometric functions. Okay, let's move on to the next part, which is the trigonometric functions. So now let's dive into the trigonometric functions. Okay? So what are the difference? The difference is, just now we've learned about the definition of the trigonometric ratios, right? That you have learned from secondary school. Now let's dive into the trigonometric functions. Okay? So recall that what is function that you have learned from chapter 2. Okay? So function is a relation, right? Which only consists of one-to-one and many-to-one. And another thing is, a function can be represented by the notation, but usually we represent it as equations. So inside the Cartesian equation, you must have the x and the y. Yeah, correct. So now, how to represent a sine function? Okay. So let's focus about an ordinary sine function and the cosine function, which is y equals to the sine. Okay, sine we put it as sin with an x inside. Alright. Meanwhile, for the cosine function, which is y equals to cosine x, usually we can pronounce it as cos x. Alright? That represents cosine. Right? So, yeah, let's describe about the what is the pattern of the sine function in the Cartesian graph. So it is a sinusoidal wave, right? As you can see, as well as the cosine. Okay, so we can say that both graphs are the continuous. Okay, because of endless. So which means that the domain, as long the x must subset to real numbers. Alright? So what is the range? Range is from -1 to 1. Why? We must follow the definition of the sine and cosine. Okay, let's recall again. So what is sine? Sine is the opposite of a hypotenuse. So as we know that hypotenuse must be the longest length among the right angular triangle, right? So which means that in the sense of mathematical interpretation, sine and cosine must only approach until 1 in magnitude. Okay, no matter regardless of their sign, positive or negative, sine and cosine do not exceed 1, right? Okay, following the definitions. So yeah. Okay. And the period, what is the period? Is actually a cycle. So you will learn this in physics, okay? Stay tuned for my subsequent videos. So what is the period in a complete cycle? Okay? Or you can it's so called a complete oscillation. Alright? Which is until 2 pi radians or 360 degree for the both graphs. So as you can see that sine graph has a sinusoidal wave, cosine graph also has a sinusoidal wave, but only has 4 quarter cycles of the sinusoidal wave. So we can explain by using this relationship. Okay? So following the transformations, if you shift pi over 2, which means that you shift this sinusoidal graph to the left hand side. So this is known as the translation. Okay? By moving the pi over 2 units for x direction. Alright? So you will get the cosine graph. If otherwise you convert the cosine graph back to the sine, which is minus pi over 2, which means that it has a translation of pi over 2 units to the right hand side. Okay? So therefore, how to relate sine and cosine, which is only involve the exchange of the quarter cycle by pi over 2, because pi over 2 represents 90 degree, right? So please remember this relationship between the sine and cosine because of their same patterns of the graph, which is sinusoidal wave. All right, which is you have a cycle which has a peak, and the below also has a peak. All right. So let's identify each of the properties of the sinusoidal graph. So the distance, I mean the coordinates, that is from the center, from the axis of the center axis to its maximum, we can call it as amplitude. Alright, so each graph, I mean each point that lies into the sine graph, okay, if you move now in this way, and this distance, vertical distance, we can call it as displacement. But in mathematics, in practice, we don't learn this. We only approach until amplitude and period enough. Alright? So I have summary for you. I have the summary between the sine and cosine for you. Please go through by yourself. Okay. Yeah. So for the cosine graph, it is from the 1 move until to their minimum range. I mean the minimum value of the cosine, and then it goes upwards and back to its original and maximum value. Alright. So for the ordinary cosine graph, it is up to down, down to up again to complete a cycle, because its period is 2 pi as well. And what about the amplitude of the cosine function, which is exactly the same as the sine? Because as I said before, turns out the cosine function is converted from the sine function with the with the transformation of the pi over 2 units, right? Okay? So this distance is the amplitude for the cosine graph. Alright? So in physics, you have to define what is amplitude, what is period. But in mathematics, we don't learn this. Okay? So everyone is curiousing that why cos minus x equals to cos x. So imagine that, as you see, this resembles the quadratic function, right? Okay, why is this the case? It's because of, in the cosine function, it consists of quadratic functions, or the higher polynomial functions. This one we can call it as Maclaurin series. This one you will learn in the further mathematics paper 2. Alright, for the pure mathematics 2. Okay, as I implied over here, imagine the cosine function as the quadratic function for this interval. Alright. So I'm not going to go through this and this for you. Okay, please read through by yourself. So if you have any questions, just reach out to me. Don't be shy. Alright. So yeah, let's move on to the tangent functions. So how to represent a tangent function, which is y equals to tangent, which is tan, not the surname of Tan, okay, which is tangent of x. Okay, follow my pronunciation, tangent x. So I know that everyone was confusing about the gradient of tangent, which is a line, and as well as the tangent functions. So actually they are almost roughly the same thing, because for the tangent function, it is almost like the gradient function, right? It is closely related to the gradient. So this one, we will cover this for you. Alright? I will cover this for you later. Okay, in the tangent functions, it is not the continuous functions, because to define the tangent functions, it only accepts the domain of x equals to for the domain, as long as the domains are all real numbers, except for the x equals to pi over 2 or pi over 2 plus n pi. N pi means you plus how many half cycles. So this dashed line, we can call it as asymptotes. Okay? Which means that the graph does not touch that line. Okay? Because if you approach this line, it does not define the tangent functions. Alright? That's why this is so-called asymptotes. Alright? So what about the range? The range is from negative infinite to the infinite. Alright? Because as you can see that no matter how high it moves upwards, it still cannot approach the vertical asymptotes over here. So why tangent negative x equals to negative tangent x? Because of it is an odd function. Oh, sorry, I forgot to imply you that y sine negative x equals to negative. So it is an odd function, whereas the cosine function is an even function because it resembles the quadratic function. Okay, so quadratic function has the highest power to 2, right? The variable raises to the power 2 that that includes inside the Maclaurin series of the cosine, right? So now is the time to explain the reason of the tangent x tangent function is an odd function, because this is the reflection, right? So if you reflect from here to here, where this is the axis or the reflection, so your tangent graph will become like this. Okay? So if you reflect the tangent function beside the tangent functions, it also turns out in this type of pattern of the graphs. Alright? So yeah, this is the simple explanations for these 3 trigonometric functions. Alright? As long you still need to recall and flashback functions and relate the functions to the trigonometrics to form trigonometric functions. Alright? So yeah, this is the part of segments for the introductions for the trigonometric functions. So it's still the same, the first subtopic for this chapter. So yeah, let's continue to the transformation for the transformation of the trigonometric graphs. Okay. Okay, guys, let's dive into the transformation of the graphs, but the graphs are trigonometric functions. All right. So before we dive into the trigonometric graphs, the transformation of the trigonometric graphs, let's recall what you have learned from chapter 2. All right. So in chapter 2, cumulatively, you've learned 3 transformations. The first, translation, reflection, and the stretch. Right? So actually, it is also valid, and it can apply into the trigonometry functions. Alright? Because this fx is valid for all types of functions. Alright? Even in the exponential functions. Let's say, okay, this is my best examples. So for the translations, what is the negative a? Which means the translation for the a units to the right hand side. If otherwise, if you put it as positive over here, x plus a, you will move a units to the left hand side. So as I emphasized before, vertical transformation and the horizontal transformations are opposite mostly. Why am I saying mostly? Because it has 2 over 3 of the transformations to agree that x and vertical and horizontal transformations are opposite. Alright? So for the plus b beside the function, which is basically it moves b units upwards. Otherwise it is b units downwards. Alright? So for the reflection, okay, if you put the negative beside the entire functions, which means you reflect on the x-axis. Okay? If you put negative beside the x, or it's so-called replacing the x as negative x, it undergoes the reflection on the y-axis. Alright? So for the stretch, if you multiply a beside the entire functions, it is a stretch parallel to the y-axis, okay, in y direction, where a is a scale factor. Okay, see, I've abbreviated scale factor as SF. So from now on, I'm going to say it as SF. Okay, so that you will know that SF represents scale factor. Okay, if you replace the x as the ax, it undergoes the stretch parallel to the x or in the x direction, where 1a is the scale factor. Alright? So before we begin the transformation of the trigonometric graphs, I have the prompt tips for you. So in the actual or external examinations, you need to sketch at least one cycle. Alright? Unless the question required the intervals and you must obey it. So let's say sketch the sine graph by this interval 0 to pi. So you must only sketch from 0 to pi only, following the particular trigonometric functions that given for you. Alright? So the most essential is you must obey the questions in the external exam. Okay, especially we need to watch out the how does the interval required. Okay, I mean how does the interval require you to draw the particular trigonometric graphs. Okay, so let's get started from the transformation from sine function. So for the translation in the x directions, if you replace x as x minus a, which means the sine x minus a, it means that you move a units to the right hand side. You see, it is valid to apply from the previous theta inside here. Okay? As well as the right hand side one. Okay. Otherwise, if you x plus a, it moves a unit to the left hand side. So this entire sinusoidal curve moves to the left hand side within this distance. Okay? Where the x coordinate over here is negative a. So if you are not understand enough, I will visualize for you via Desmos. Okay? So for the translation for the y directions, if you add a or minus a, add a, which means that the sine a plus a, okay, turns out the result of the sinusoidal curve moves upwards by a units. Okay, where this coordinate is a. Okay, sorry about that. This is a, and when this coordinate is negative a. Okay, since the entire function of sine x minus a, which means that this graph moves downwards by a units. Okay, shift downwards like this. So this is how does the transformated graph look like. Okay. So now let's move on to the next transformation. Next transformation, which is reflection. So as the result of sine function is an odd function, okay, if you multiply the entire sine function with a negative beside, you will transform from this to this. Okay. So why we can say that all of these are the same? Because let's focus on the reflection on the x-axis. So which means that this is the center of axis of the reflection. You reflect this half cycle to the negative interval, negative quadrant. Meanwhile, this one exchange upwards. So you will form this kind of the reflected sine graph. Okay, what about for the reflection on the x-axis? Which means that you put negative x inside the sine function, okay? So which means that since you know, given that the sine function is a continuous function, so it has a complete cycle over here, whereas for the negative quadrant, it has a negative cycle like this, and you reflect here. Meanwhile, for the positive quadrant, you reflect to the other side. So turns out the reflected graph of the sine on the y-axis will become the transformated graph, which is exactly the same as the reflection on the x-axis, right? So please remember the fact, and this is the best evidence to prove that negative sine x equals to sine of the negative x. Okay? As I implied before, sine function is an odd function. Okay? We can prove this by using the reflection. Okay, the transformation. Alright? So now let's move on to the last transformation for the sine function, which is the change in amplitude. Okay? Which is parallel to the y-axis. So if you multiply the a beside the entire function of sine a fx, okay, provided the modulus of a must greater than 1. So which means that you stretch the sine graph, okay, to by a times. Okay, because initially an ordinary sine graph has amplitude of 1. Okay, 1 in magnitude. And if you stretch the sine graph, which means you multiply the original amplitude by a times, where a is a scale factor. So this is the results after the stretch by scale factor of a. So for the another side, if your a is 0 to 1, okay, so a is likelihood 0 point something. So you will transform this to this. So this is basically the compression, which means you times the sine function by a times for a is from 0 to 1. Okay, this is so-called amplitude compression. Alright, so you compress like this. So for the a, so this a refers to their value is less than 1. Alright. So this only changes. So for the stretch in y-axis in the sine graph, it only changes its amplitude. So whereas if you have a stretch transformations by replacing x as the ax, okay, it undergoes the compression with a scale factor of 1 over a. So my implication was right. Because as I said before, the horizontal and the vertical transformations are opposite. And this is clearly evident. This is the best evidence. Alright. So before you transform the sine graph, you need to take a look at the original periods. Okay? So if you want to change the new period, if the question asks you to find the new period, which is ordinary of the 2 pi times 1 over a, or divided by a. Okay, or 360 degree times 1 over a. For the a subsets to real numbers. Okay? So as you can see that ax modulus of a greater than 1, and this is the ordinary sine graph. So it transforms into 2 complete cycles. So why? Let's say if your a is 2, which means that you need to make 2 cycles to complete the graphs until 2 pi. Okay? A is 2, which means that you need 2 cycles to approach 2 pi. So this is the examples. Alright? So for the A is 0 to 1, which means that it is x. It is the horizontal stretch. Okay? From these ordinary sine functions to this. For each of these coordinate multiplied by a times. Okay? So yeah, I think the rest of the context over here you can go through by yourself. So I know that only explaining the sine function transformation by using using the way of the lecture notes is not sufficient. It's insufficient. So let's use the Desmos for the further visualization for your understanding. Alright, so here is the visualization of the transformation of a sine graph via Desmos. Okay, so as you can see that the green dashed line over here represents this represents the pi, and this is the 2 pi. Okay, and this is for your understanding. Okay, so here is your ordinary sine graph in the sinusoidal wave, as you can see over here. So here is the peak, which is pi over 2 1, and where this distance is amplitude. And what about this? This is the pi 0. Okay, so the sine x only equals to 0 where your x is 0, pi, 2 pi. Okay, or your domain is n pi, where n equals to 0, 1, 2, 3, or something, and so on. Okay, so let's begin from the transformations. So for the sine functions, if it undergoes the vertical transformation, okay, we can only vary the d. So if you vary it by 1, so by right, your graph should look like this. Okay, as you can see that the graph moves up by 1 units. Okay, so what about the below one? So as you can see that all the sine graphs moves down by 1 units, but the amplitude still doesn't change. Okay, so let's describe the x transformation and see. So x transformation means that the x plus the c, right? As I point over here. So if you move the c to the left hand side, let's say I move to 1, which means that the sine graph moves to the left hand side. Okay? Otherwise, if you change your c to the -1, it moves to the right hand side. So yeah, it is exactly the same as the transformations for the other types of functions. So this is clearly evident that the transformation that we have learned from chapter 2 is valid for all functions. Okay? So yeah. So now is for the reflection. If we change the a to negative, so as you can see that it undergoes the reflection, just that the period does not change. Okay? As you can see that the maximum point becomes the minimum point, and the minimum point becomes the maximum point. Okay, this is what am I trying to imply. Right? So what about the negative one? Okay, let's change the a back to 1. Why do I have to put the a as 1? Because if you put a 0, which means that this is not the sine function already. Because of the 0 has devasked the entire sine function. Right? So let's try the b visualize the sine negative x. So we replace the b as -1. So as you can see that the sine negative x looks like this. So it is exactly the same as the um, reflected sine graph on the x-axis. So now it's the reflection on the y-axis, okay, which is exactly the same as the reflection for another dimension. Okay, so yeah, let's change it back. So now let's visualize the stretching. So let's change the a instead of 1. Let's say I change it to 4. So as you can see that the amplitude of the ordinary sine functions, if you multiply by 4, the amplitude changes by 4 times. 4 times from the original amplitude. As you can see over here. Okay? Each of these two turning points, the y coordinates of the both turning points will become 4. 4 times from its original amplitudes. Okay? So yeah, let's change the a back to 1. And let's change the b to an integer. Okay, let's say I change it to let's say 2. Let's say I change it to 4. So as you can see that this is 2 pi. Okay, an ordinary sine functions, I mean the ordinary complete cycle for the sine functions, as you can see that it requires 4 times to complete a cycle. Okay, 1, 1, 2, 3, and 4. Okay, which means that these sine functions, a complete cycle, must be divided by 4 times to approach 2 pi. Okay, so this is how does the stretch in x direction work. Okay, yeah. So next I'm going to explain about visualize how does the transformation work for cosine functions. So for the cosine functions, it is exactly the same as the sine function. Just the cosine function is a quarter cycle difference from the sine function. So let's dive into the translation in x direction for the cosine function. So if you replace the x by x minus a, which means that you move the cosine function, the cosine graph, to the right hand side by plus a. Otherwise, is the cosine graph moves by a moves a units to the left hand side. So I'm not going to explain this too much. Okay? Because the transformation of the functions are all valids. Are all valids for all functions or any functions. Okay? So for the translation in y direction for the cosine functions, if you add a, it moves upwards by a units. Otherwise, it moves downwards by a units. Okay? So for the reflections, negative fx, which means the negative cosine of x, okay, it is a reflection on the x-axis, which means you reflect the entire function. So for here, for the first quadrant cycle, you reflect downwards. And for the negative graphs, you reflect upwards. Okay? Do it the same thing for the last quarter cycle. So turns out the negative cosine x will become like this. Okay? It is like a bell-shaped curve, right? But the f of negative x is different from this negative cosine x. So since cosine function is an even function, okay, as I implied before, cosine x resembles the quadratic function because of their sinusoidal graph for a half cycle is like a quadratic function because of they have the power 2. Okay? They are variables that raises to the power of 2. Okay? But this is not the primary reason. The main reason is, the main argument is the cosine negative x equals to cosine x is because of you reflect the cosine graph on the y-axis, you reflect from here to the negative quadrants. Okay? And the negative quadrants you reflect to the other side. So which means that for the negative negative 4 quadrants on the left hand side has the same pattern of the graph for the 4 positive quadrants on the right hand side. Okay? So this is clearly evident that the cosine function is an even function. Alright? Apologize that I need to repeat many times for your understanding. Okay? So the same thing is, if you have any questions, just reach out to me. Don't be shy without hesitation. So let's move on to the stretch of the cosine functions. So first is the amplitude change, and another one is the compression, is for the period change. So if you multiply the entire cosine function by a times, which means the cosine function times a, where a is the scale factor. So provided that for the modulus of a is greater than 1, okay, it stretches the graph. It stretches its amplitude by a times from its original amplitude. So sometimes the original amplitude is not 1 because of their variety of the questions asked in your external examinations. This one you need to do more exercises, okay, to have a strong grasp in the trigonometrics. Alright? So yeah. Otherwise, for a from 0 to 1, you will have the compression of the amplitude. Okay? So for the period changes, for the cosine function that is parallel to x-axis, which means that you replace x by ax, you will get the scale factor of the 1 over a. Okay? And also the original period of cosine function is 2 pi and 360 degree, as we discussed before. So to get the new period, you need to take the 2 pi, since the 2 pi is a complete cycle, divided by a, as well as the 360 degree. Clear? Yeah. So for the a, modulus of a is greater than 1, it undergoes the compression of the graphs in period. So let's say you have 2, which means that you need to do how many a cycles to approach 2 pi. Okay? So for the a is 0 to 1, you will have a stretching in period. So which means that for the pi and the 2 pi must multiply by a. Okay? So yeah, let's dive into the visualization of the cosine graph via Desmos. Okay, so come back to the Desmos graph. So as you can see that this is the sinusoidal graph, right? Just that it is with the quarter cycle difference from the sine graph. Okay. So now this is the segments of visualizing the transformations for the cosine functions. Okay, referring to its graph. So it is similar to the sine graph, just that cosine is an even function. So let's start from the translation of the cosine graph, right? So let's vary the y, the d first, okay, because the d refers to the translation for the d units, okay? So let's vary the d as 1. So as you can see that the cosine graph moves upwards by 1 units, okay? If otherwise, if you slide the d to -1, it, it turns out that the graph shifts downwards by 1 units, okay, by 1 unit. So this is clearly evident that the cosine graph for the if you add or minus d, it will change the graph vertically. All right. So let's recover d back to 0. Okay. So for the x, let's vary the c. Okay. If you change the c to -1, what will you observe that the c moves to the right hand side by 1 units. Okay. If otherwise, if you let the c become negative, I mean positive, the graph shifts horizontally to the left hand side by 1 units. Okay? Like this. Alright? So let's get back to 0. So now is the visualization of the reflection for cosine function. So let's start from the reflection on the x-axis. Okay? Reflection on the x-axis means that their y, um, their range will reflect. Okay, which means that the value of cosine over here will reflect to negative. Okay, so let's change this a to negative. So you will see that it undergoes the reflection. All right, so this is the 2 pi. Originally, for an ordinary cosine graph, for the complete cycle, it places at the 2 pi 1. Okay, coordinate of 2 pi 1, it changes its y coordinate to -1. As you can see, the 3 turning points for the cosine function graphs of functions. Okay, so let's change back the a to 1. So still the same, you can't let the a become 0. If you let a become 0, it is not a trigonometric functions. Alright, because the value of a becomes 0, it devises the cosine function as well. Like this. So let's vary the c. Sorry, it's b. So yeah, let's change the b to -1 and c. So you can see that for the b -1, it remains the same as its ordinary graph. As I said before, this the peak over here resembles the quadratic function because of the presence of the Maclaurin series, right? So yeah. So let's change back the b to 1 in order to define its cosine functions. So let's dive into the stretch. Okay, the transformation of the stretch. So for the uh, stretch parallel to the y-axis or in the y directions. So instead of putting 1 over here, you can, let's say I want to change to 2. So let's change the value of a to 2, slide it in this way to the right hand side. So we can see that the two has changes. I mean, its amplitude changes by 2 times of its original amplitude. Okay? So if otherwise, I slide into 0.8, which means that it is 0.8 times of its original amplitude. Okay, this is the amplitude change, which is so-called the stretch in y directions. Okay, where this value is the scale factor. Okay, as well as the sine functions just now. Okay, so let's vary the b. So let's change the b into let's say 3. Okay, when you change the b into 3, which means that it requires 3 cycles to approach 2 pi. Okay, so you can see that an ordinary cosine function, this from up, down, up, first cycle, up, down, up, a second cycle, up, down, and up, third cycle. Okay, so it is the stretch parallel to x-axis or in the x direction with the scale factor of 3 for the cosine function, which means that it requires 3 cycles to walk until 2 pi in the x coordinate. Okay? So that's the end of the visualization of the transformation for cosine graphs. Okay? So let's move on to the transformation for the tangent graphs. Oh wait, sorry about I missed something. So if you change your b to less than 1, so you can see that, let's say I change to 0.5. So which means that 2 pi, its period is 2 pi divided by 0.5, which means that it only requires half cycle to reach 2 pi in x coordinate. Alright, so yeah, this is how does the stretch work. I mean the transformation work for cosine function. So now it is the time to discuss the transformation for the tangent graph. Alright, let's proceed to the last trigonometry function, which is the tangent function. Just that tangent function involves transformation. Alright, so as I implied before, the transformation of the functions is valid for all the functions. Okay, which means that you can apply this. You can apply the whatever these 3 transformations inside any kinds of functions. Alright. So let's targeting about fx equals to tangent x. So let's dive into the first transformation, which is the translation, but in x direction and y direction respectively. Alright. So for the x direction, if you replace the x by x minus a, which means that the entire non-continuous tangent graph will move to the right or shift to the right by a units. Okay? If otherwise, the graph moves to the left hand side by a units. Alright? So yeah. So for the translation in the y direction, it's basically add up or minus a, or it's so-called plus or minus of a beside the entire tangent functions. Okay? So let's visualize the graph over here moves upwards by a units when it comes to plus. If otherwise, it shifts downwards by a units. Alright? So yeah, that's the simple explanation that involving translation towards the tangent functions. Okay? Targeting to their graphs. Okay. So let's move on to the reflection of the tangent functions. So as I implied before, this is the primary reason that y is tangent function and odd function. Okay? So, when you put a negative sign beside the entire tangent functions, what it happens? Okay? This tangent graph will reflect on the x-axis. Okay? We are explaining about this. So which means that the negative, the third quadrant and the fourth quadrant, I mean the negative graphs in the negative quadrants reflects upwards on the x-axis. Okay? And meanwhile, the positive graphs reflects downwards, also on the x-axis. Okay? So turns out your tangent graph will become like this after the reflection. As well as for the negative x inside the tangent functions. So, as you know that tangent graph is the non-continuous, following their definitions from the sine and cosine. Okay? So, reflection on the y-axis, we are explaining about this, which means that this line, which is the y-axis, okay, the reflection on the vertical dimension. So which means that this graph, the original graph of tangent, it also has a negative interval and it continues until its infinity. Okay, which means that the entire tangent graph from the negative switches to the positive, and the positive one in the x direction switches to the negative. Okay, because all of these graphs reflect on the y-axis. Okay, because we want to reflect the domain, right? Positive becomes negative and negative becomes positive. So yeah, it makes sense. So this is so always remember, when it comes to sine function and tangent function are both odd functions, it's because of the reflection. Okay, the results of the reflections are both the same or remains unchanged. All right, so this is the proper and valid and suitable explanations. Okay, so nothing to explain further over here. So let's proceed to the last transformations for the tangent functions. Okay, so apologize that there is a spelling mistake over here, but as long you get understand about this. So for the amplitude change, which means that this is the stretch that is parallel to y-axis or in y direction. Okay, so when a is the scale factor. Sorry about it. I think it must be something wrong about this note. But you need to write it by yourself, okay? For your understanding. So when it comes to a times multiply beside the entire tangent functions, okay? So this transformation describes there is a stretch parallel to y-axis with a scale factor of a. So a has two scenarios. First scenario, the modulus of the a is greater than 1. It means that the magnitude of the a is greater than 1. Okay? So I give it an example. Let's say if a is 2, which means that the tangent graph has to be stretched until the value is a. Okay? When you extrapolate the a, as long the x inside does not change, okay, the extrapolation of the x coordinate from the y coordinate A must be pi over 4, where pi over 4 denotes 90 degree, right? Okay? So as we know that the tangent pi over 4 is 1, since it only involves the stretching of the entire tangent functions, which means that the extrapolation of the pi over 4 to its y coordinate must be equal to A. Okay? As well as the another scenario when A is in between 0 to 1. Alright? So this is the result of the compression of the amplitude, which means that you diminish the amplitude from its original amplitude. Sorry about that. Since tangent x is not the continuous, which means that tangent does not have the original amplitude, but it has the best the best point to describe that the tangent graph has the stretching transformation. Alright, by extrapolating the pi x coordinate of the pi over 4 to 1. Okay, where 1 is the original value. Okay, we can call it as original values of the extrapolation of pi over 4. But instead we can call it as original value enough. Alright. So yeah. So when it comes to the A is less than 1 but not to 0, it becomes like this, where A is less than 1 after the transformation, but as long the x inside the tangent does not change, the extrapolation of the A must be pi over 4, or pi over 4 plus n pi. Okay? So for the compression, it is also about the stretching, but it is parallel to the x-axis. Okay? So when you change the x to ax, which means that this is the stretch parallel to x-axis with a scale factor of 1 over a. So for the tangent graph, its original period is 180 degree, right? Where the new period is 2 pi divided by a, or 360 degree divided by a. Okay? So for modulus of a is greater than 1, which means that because of the original cycle of the tangent graph is 180 degree, a cycle means a first cycle, and you repeat for the second cycle. So here is your first cycle from 0, right? So which means that your graph will compress like this as long as the asymptotes will be influenced. Okay? Because of the transformations, the stretchings for the x direction. Okay, if otherwise, a is in between 0 to 1, which means that you expand, you make the tangent graph bigger or expand it widely. Alright? So for the coordinates of intersections and the asymptotes, all of them times a after the transformations, after the stretching that is parallel to x-axis for this interval. Okay? So yeah, I think we have one more segment away before proceed to the next subtopic, which is the trigonometry identities. So yeah, let's proceed to Desmos for the visualization of the tangent graphs. Okay, its transformation. Okay, here it comes to the visualization of the transformation for the tangent graph. So this will be the last segments. I'm using the Desmos. Okay. So as you can see that this dashes line denotes the asymptotes, which means that for the tangent functions, the graph does not meet the asymptote. It's because of this x coordinate and the following x coordinates are all undefined for the tangent functions. Okay. So why I'm intend to plot this coordinate and um, creating the green vertical line is because of you extrapolate the x coordinate of pi over 4 to 1. Okay, its original value is 1 from pi over 4. Okay, for your understanding. So let's start the transformation. Let's start the visualization of the translation. So let's start from the translation in the y direction. So let's vary d. Okay. So let's change the d to 1, which means that you add by 1. So what will you observe that from this original graph, it shifts upwards by 1. So as you can see that for the extrapolation of the pi of 4, its value changes to 2. Okay? So this proves that the tangent for the tangent functions in for the the translation in the one direction for the tangent functions, it is it moves upwards when the d is positive. If d is negative, it moves downwards. So let's show. I show you here. So if you move down, if you shift the tangent graph by 1 unit, by right it should be like this. Okay. So for the extrapolation of the pi over 4, its value will become 0. Alright. So let's visualize the translation for the x direction in the x direction, which means we vary the c, the value of c. So let's change to let's say we change the c negative, so we can change to -1. So as you can see that the tangent graph moves to the right by 1 unit. Similarly, simultaneously, all of these asymptotes also shift to the right by 1 unit. Okay? If otherwise, if you let c become positive, the tangent graph moves to the left by 1 unit. As well as their asymptotes also shift to the left by 1 unit. Okay? So generally, for the translation in the x direction, as the tangent, the graph, its tangent graph moves, the asymptote also moves. Okay? So yeah, let's go back to 0 for the c. Now let's vary it. Let's visualize the reflection of the tangent graph. So let a becomes negative over here. So what you can observe that the original tangent graph will reflect in this way, as I mentioned just now. Okay? Because it reflects on the x-axis, the negative moves upwards, reflects upwards, and the positive one reflects downwards. Okay? Similar to the reflection on the y-axis. So what you can observe that the reflection on the y-axis has the same transformated graph as the reflection on the x-axis, as the graph is shown over here. Okay, so this proves that tangent graph is an odd function. All right. So if you find this useful, I glad to hear that. But if you have any doubts or any any questions, don't hesitate to reach out to me. All right. So let's recover back the values of a and b to 1 to define the tangent graph. So return to the original tangent graph. Let's visualize the stretching of the tangent functions. Okay, so instead of letting a become 1, let's say I change a to 3. You see what happens to the tangent graph over here. So for the same extrapolation of the x-coordinate, if you extrapolate upwards and you intersect the pi over 4 with the tangent graph, as you can see that this is the original coordinates. Okay, from the 1 to the 3. So which means that its original value 1 times 3. Okay? To say that the tangent graph undergoes stretching in the y directions, where 3 is the scale factor. Okay? So let's get back to 1. Okay. So now let's visualize the final part, which is the compression of the tangent graph, which is the stretch in the x direction, which mainly changes its period. So let b becomes 2. So what will you observe that you need to undergo 2 cycles to reach the pi, which means the 180 degree. So the original coordinate of the pi over 4, okay, I mean the extrapolation of its y coordinate from the pi over 4 will become an asymptote. All right, I mean this vertical line, after you transform, let's say the b equals to 2, it will become asymptote. So this implies that as the period changes, the asymptote also changes because it affects the cycle. All right. So let's say I put b is 2. It means that from 0, you need to have 2 cycles in order to approach the pi. Okay? So let's change the b to less than 1. So what will you see that you just need a half cycle to reach 180 degree. But for the b is less than 1 but not equal to 0, the transformations, I mean the cycle widens. Okay, so this is the best and simple explanation for the stretch in the x direction. Okay, so let's say, so here I put b is 0.5, which means that we just need half cycle to reach 180 degree. Okay, sorry, not 180 degree. We just need a cycle. Yes. I think I was right, because this is the half cycle to reach 180 degree. If we make a full cycle, we just reach 2 pi. Okay, so yeah, I was right. And apologize that I forgot to visualize the stretch in the y direction. What if the a becomes less than 1 and greater than 0? So let's recover the b to 1 and a is less than 1, let's say 0.5. So what we will observe that this is the original intersections of the pi over 4 with the tangent graph. So as you can see that its value changes by half. Okay, which is basically the scale factor multiply its original value. I mean the original y coordinate extrapolation from the pi over 4, where pi over 4 is the x coordinate. Okay, so yeah. Okay, it finally comes to the end of the visualization of the 3 trigonometric functions graphs. I mean the graphs of these 3 trigonometric functions. So let's get back to the lecture notes to proceed to the next subtopic. Okay, we are finally moving on to the next subtopic, which is the trigonometry identities. So apart from to have a strong grasp of the trigonometry ratios based on the each respective definitions and the graph of the functions with the transformations, it is crucial that we need to know about the trigonometry identities. So as you can see that these two formulas exist in your MF19, okay, but I think it's still essential to know how does it come from. Okay, so as I write the fact over here, I need to make a disclaimer that these two, since I was implied that these two exist in the MF19, so the meaning from here, you have to remember these identities to answer any trigo proof only in AS, which means that you need to use only these two facts to answer the trigonometric proof in your AS examinations, especially for the pure mathematics one. Alright, so let's discuss the first formula, which is the tangent theta equals to sine theta over the cos theta. So this is exactly equal. So by right, I should write a triple equal sign, but usually we put an equal sign with two parallel horizontal straight line like this. So how to prove tangent theta equals to sine theta over cos theta? This identity from your MF19. So write out all of these definitions of the trigonometry ratios, and you may draw a right angled triangle, because right angled triangle is closely related to the trigonometric. Okay, and you have x, y, and r, where r is the hypotenuse, x is adjacent, and y is the opposite. Okay, where this is the reference angle in the right angled triangle. So given that the sine theta is the opposite over the hypotenuse, cos is adjacent over hypotenuse, and what about tangent? Tangent is opposite over adjacent. Okay, so how to prove it? How to prove it? Let the tangent theta equals to y over x as your first equation. Okay, so sine theta equals to y over r. But I want to get rid away the terms y and x, right? So move, convert this equation into the y as a subject in terms of r, as well as for the x also in terms of r. Okay, label these two as equation 2 and equation 3 as respectively. So now you substitute the second equation and the third equation into the first equation that you have implied here. So after the substitution and the simplification, by cancelling the r at the both numerator and denominator, so yeah, you have successfully proved it. Okay, to prove that the identities of tangent theta equals to sine theta over the cos theta. But no worries, because this formula exists in your formula bullet MF19. Okay, so here is the prompt that how to identify the sine square. Sine square means the sine theta bracket square, as well as for the cos theta and the tangent theta. So this is the best symbol for your understanding. Okay, to avoid candidates to be misunderstood for these three common expressions. Okay, so the next identities that also exist in your MF19, which is the sine theta plus cos squared, sine squared theta plus cos squared theta equals to 1. So this is so-called Pythagorean identity in the trigonometry. All right. So why do I have to call it as Pythagorean identity? It's because of you need to relate the trigonometrics as well as to the Pythagoras theorem. So this is the reason. Use the fact of the Pythagoras theorem, x squared plus y squared equals to r squared. Okay. Also, I can paraphrase into the square of the adjacent plus the square of the opposite equals to the square of the hypotenuse. Okay. So label it as the fourth equation. Okay, from the second equation, you square the equations at the both sides to get y squared equals to r squared sine squared theta, as well as for the x squared equals to r squared cos squared theta. Okay, so it's basically squared at both sides. So this is your fifth and sixth equations respectively, and substitute both of them into the equation form to get rid away the term r. So as you can see that the x is replaced by cos r squared cos squared theta, and y squared is replaced by r squared sine squared theta. Okay, as you can see that each term has a common factor, which is r squared. So now you factorize the r squared outside and you cancel the r at the both sides of the equations, and therefore you will get it. You will obtain the identities of the sine squared theta plus cos squared theta equals to 1. And it's so-called Pythagorean identity. Okay, so yeah, it's proven. So in your AS examinations, you won't ask to prove the trigonometric equations that involves the reciprocal of the trigonometric, because these three functions, secant, cosecant, and secant, sec, cosec, and the cotangent. This one you will learn in A2, not in AS. So don't worry. Okay. So now, let's move on to the strategies of solving the trigonometric equations, but involving the multiple angles. So given that you by right you should solve like in the sine theta equals to the k, where k is a real numbers, right? So find its inverse functions. So what does the inverse function mean? It means that the sine theta, if you move to the other side, you will get theta equals to arc sine. Okay? The above is a negative 1, but it is not equal to 1 over sine k. So this is the common mistake that many candidates might make. Okay? So don't repeat the same mistake again. Okay? Since it is an inverse function, just move to the other side. Then it's called arc sine, arc cos, arc tangent. Okay? So find its inverse function for the reference angle. Okay, first you find the reference angle that is in the interval of the first quadrant. Alright, next you find the other possible solutions. Okay, from the required intervals, following the required intervals from the questions. Okay, you must comply it. So as I implied before, we need to have a strong grasp of the all, sugar, tea, and ASTC. Okay, in the first 4 quadrants. So S means it is positive on the second quadrant. T means it is positive on the third quadrant. C means it is positive on the fourth quadrant. So you must bring this fact and apply into solving the trigonometric equations. Okay, find all the intervals and then you convert from this theta, but let the theta as the subject. Because sometimes the theta is not always the theta or not the x, but it can come out in like 2 theta, 3 theta, and even 4 theta. Okay? So you must remain the result of the inverse function of the trigonometric. Okay? And then find the other solutions from the other intervals. Finally, find all the solutions from the required intervals from the questions, and finally you transform into a single theta. Okay, a single what does the question want? Okay. All right. So yeah, I think we have ended the discussion of the solving the trigonometric equations that involving multiple angles. So it's useless for us to lecture about these strategies. Instead, we can use the exercises for the further understandings for you. Okay. Alright, let's proceed to the last 2 subtopics, which is the inverse trigonometric functions. Alright, so I may apologize that solving trigonometric equations that we discussed just now is one of the subtopics. Okay, so now it comes to the 4th subtopic among this chapter, trigonometry, which is the inverse trigonometric functions. So, as I implied before, what is the inverse function of the trigo functions? We can call it as arc sine, not sine power negative 1. Okay? So, these are the common mistake that every student might make, which is 1 over sine x or cos x or tangent x is not equal to the arc sine of the x. So please be aware about this statement. Okay? So that you won't repeat the common mistake again occasionally. Alright? So, as we know before, inverse functions has the definitions of what it is one-to-one functions. It means that only an object is mapped to their particular and sole image, right? So for the inverse trigo one-to-one functions, in order to define the inverse functions, it requires the sacrification of some domains, okay, to define its validity. So what does this statement means? Basically, it means, sine, for example, arc sine, not arc sine. The ordinary sine function is continuous, right? And the domain is as long its domain is real numbers. So now it comes to the inverse trigo, its domain and range is exchanged after it is taken inverse function. Okay? So this is your original sine graph from negative pi over 2 to pi over 2 like that. Okay? Because only these segments of the graph, this interval, does not have many to one functions. Okay? Why does it say so? Because this is the first half cycle. As you can see that this is the many to one functions. For the another side, it's also many to one functions. But we only want the one to one functions. So which means that only the domains of the sine from pi over 2, from negative pi over 2 to pi over 2 can be defined to its inverse. So this is how its inverse looks like. Okay? From negative 0.5 pi to 0.5 pi. So this is the range of the inverse. Okay? So let's recall that the domain of a function fx equals to the range of its inverse function, and the domain of the inverse function equals to the range of the function. So using these two facts inside these trigonometry functions, alright, I mean particularly its sine function, which is basically exchange the domain and the range numerically. Okay? So I think this domain and the range will exist in your MF19. So no worries to say you are no point to how to find its domain and the range, right? Okay? At least MF19 that you have it during the external examinations to provide you the ideas in order to answer the particular questions. Okay? So, we want to relate the inverse function and the function by a center of its axis. So, which is basically a reflection, like a reflection. Reflection on the line of y equals to fx, where its angle of elevation over here is exactly 45 degree. Okay? So which means that at a sole intersection of the fx and the inverse fx must pass through an origin. Okay? Must intersect at the origin for targeting the sine functions. Okay? So this is the ordinary function fx sine equals to sine x, and when it comes to inverse, you may reflect this to this. Okay, similar as the negative part. I mean the negative graph over here that I've drawn over here, from like this reflect to the right hand side to like this. Okay? As long you have shown the sine function and the inverse sine functions has an intersection of origin at the y equals to x, the dashed line. Alright? So, yeah. So let's proceed to the next type of the inverse trigo, which is arc cos. Okay? So let's say this is the ordinary cosine functions from 1 to -1. So similarly, you still have to sacrifice the most of the domain. Only remains the first half cycle. Okay? Why should we remain this interval of domain is because of when you draw a negative over here, you can see that this graph is like a quadratic function, has a many to one relation. But to define inverse, we must use only one to one functions. So as I implied before, definition of the inverse trigonometric depends on their on the domain and the range of from their ordinary functions. Okay, so this is what its inverse function looks like. Okay, so this is the center point of intersections. All right, so you will reflect this graph from here to the another side like this. Okay, and for this side you reflect upwards. Okay, as long you need to obey the interpretation of the inverse functions must obey a reflection. Okay, where y equals to x, I mean the dashed line of the y equals to x is your center of axis. Okay, to clearly relate cos x and arc cos x. Okay, so next, let's move on to the last inverse trigonometry, which is arctangent. Okay, so as we know that an ordinary tangent graph is not continuous, so which means that its asymptote is 0.5 pi, and coincidentally this is a complete cycle. Okay, so which means that for the tangent graph only required a cycle enough to define its inverse function. Okay, so it turns out that its domain and range of the arctangents basically is exchangeable. Alright, I mean the exchangeable an ordinary tangent graph has a certain domain and the range only in this interval is exchangeable to make its tangent x to be defined. Okay, so this is your arctangent graph. Reflect through the y equals to x, the dashed line, to the other side, like this. Okay. So many students think that inverse trigo is very tough. However, no worries. As long you need to know its domain and range to draw its graph, you can refer this from your MF19. Okay, so no worries that you don't have the point. I mean, you don't have the idea to answer the questions that is regarding the trigonometrics, inverse trigonometry. Okay, so I think the the external examiner questions is likelihood for you to draw the inverse trigo graph. Okay, so you still have to grasp these three inverse trigo functions. Somehow you need to know the another advanced knowledge of the like differentiation of the trigonometry inverse trigo. Okay, so this is the best recall for you before you absorb this topic, I mean this subtopic. Okay, and yeah, the last thing is these two are the asymptotes. So when it comes to the inverse functions, it will become its asymptote, this vertical asymptote will become a horizontal asymptote. So as I drawn over here. So like this, when it goes down until it is approaching the horizontal asymptote. Okay? So which means that its graph, domain, and range will change and exchange. Also, the asymptotes will also change to another dimension. Okay? So for the inverse trigo, the inverse tangent, its vertical asymptote change to horizontal asymptote at the certain interval. Okay? So I hope you find this useful, right? So let's proceed to the last subtopic among this chapter. Alright. Had you remember that here is the mystery that how do we get gradient of 1 equals to gradient of 2, and the m1 times m2 to get negative 1, to say that line 1 and line 2 are perpendicular to each other. Okay, with this is the right angle of 90 degree. It's because of each slope line has the certain angles. Okay, so also you have known that tangent theta equals to y over x. So what you can discover that y over x is actually like a gradient, right? It means the ratio of its y coordinate distance over the x coordinate distance. So it's the same thing. So basically the tangent theta is related to the gradient of the tangent. Okay? Not tangent line is a straight line, but it's slope. Okay? So how to prove these two statements? We can just use the definitions of the tangent functions. The tangent ratio. Okay. So let's get to the mystery and what's the solution to prove these two. Okay. To make these two formulas. Okay, guys, sensible. I don't think it is the time for us to solve the mystery over here. Alright. However, I will continue in part 2 for the chapter 5 trigonometry. As I mentioned before, this chapter is considered as the long chapter. Alright. So thanks for watching. Make sure to press the subscribe button with the bell for the further updates. Alright. See you in the next video. Goodbye. Thank you for watching this video. Be sure to like and share this video and subscribe to this channel. I will see you in the next video. Goodbye.